Today we are going to see the concepts of independent sets and clique of a graph. Independent set. In independent set we have vertex independent set and edge independent set. In vertex independent set we will see maximum independent set and independent number. In edge independent set we will see maximum edge independent set and edge independent number. Independent set. What is independent set? A subset S of V, that is vertex set. The subset S of V is called independent set S of V, S of G if no two vertices of S are adjacent in G. Maximum independent set. A independent set S is said to be maximum if G has no independent set S dash such that mod S dash greater than mod S. That is, number of elements in S dash always greater than number of elements in S. There does not exist S dash, the S is said to be maximum. For example, in the above graph, S, that is independent set. Independent sets are, that is S equal to 1, S1 equal to 1, 1 is independent, and each vertex singleton vertex set is independent sets. In the above graph also, that is S equal to 1, 4. That is, the elements 1 and 4 are non-adjacent. 1 and 4 are non-adjacent. Therefore, S is independent set. S dash we consider two vertices 2, 4. 2 and 4 are non-adjacent. Therefore, S dash is independent set. And S double dash is 2, 5. That is, 2 and 5 are non-adjacent. Therefore, they are independent set. And S3 dash equal to 3, 5. 3, 5 are non-adjacent. Therefore, S3 is, S triple dash is independent set. S4 dash, that is 1, 3. We consider 1, 3. 1 and 3 are non-adjacent vertices. They are independent. Therefore, this is an independent set. We will search for any independent set with the 3 elements. We didn't get a independent set with the 3 elements for this graph. Therefore, these graphs are all maximum independent set. In maximum independent set. Next we will see the independent number. Independent number. That is, independent number is the number of elements in the maximum independent set is called independent number. That is, here the maximum independent set is having 2 elements. Therefore, the independent number of this graph is 2. Next, we will see edge independent set. Edge independent set is a set of links of G such that no two of which are adjacent in G. Maximum edge independent set, and edge independent set L is said to be maximum if G has no independent set L dash such that mod L dash greater than mod L. That is, there is no edge independent set exists such that it is having more than elements than the independent set L. Consider this example. Here we consider the edge 1, 2, that is L1 equal to 1, 2. This is independent, and L2, 3, 4, the edge 3, 4 and 1, 5 are non-adjacent. Therefore, this is the edge independent set. And L3, 5, 6 and 1, 2 are non-adjacent. Therefore, L3 are edge independent sets. Now, let us consider these graphs. L equal to the consider 1, 2 and 3, 4 and 5, 6. This is the independent set. Here, these edges are all non-adjacent. Therefore, this is the edge independent set. And 2, 3 and 4, 5 and 1, 6. These 3 edges are non-adjacent. Therefore, L dash is maximum edge independent set. Next, 1, 5 and 2, 3 and 4, 6. These 3 edges are non-adjacent. Therefore, L double dash is maximum edge independent set. L triple dash, that is 2, 6 and 3, 4 and 1, 5. These 3 edges are non-adjacent. Therefore, these are all edge independent set. We don't have any edge independent set having 4 elements. Therefore, these sets are maximum edge independent set. Next, independent number. The number of vertices in maximum independent set of G is called independent number and it is denoted by alpha G. That is, vertex independent set is denoted by alpha G. Edge independent number. Number of edges in the maximum edge independent set is called edge independent number. It is denoted by alpha dash of G. That is, vertex independent number is denoted by alpha G and edge independent number is denoted by alpha dash of G. Edge independent set is actually a matching since edge independent set consisting of the non-adjacent edges. Therefore, it is actually a matching. Hence, alpha dash of G is the number of edges in the maximum matching of G. In the above graph, the vertex independent number of G is, that is, vertex independent number 1, 3 are non-adjacent and 2, 4 are non-adjacent, 3, 5 non-adjacent. That the set containing 2 elements is the maximum independent set. Therefore, the independent number of G is 2. Edge independent number of G is 3. That is, in the above graph, these are the maximum edge independent set. The number of elements in the max independent set is 3. Therefore, independent number is 3. Therefore, edge independent number of G is 3. Next, we will see covering of G, vertex covering and edge covering. That is, in vertex covering, we will see minimum covering, minimum vertex covering, covering number, vertex covering number, edge covering, minimum edge covering or edge covering number. Now let us see the definitions. Covering of G, a subset K of V such that every edge of G has at least one end in K is called covering of G. Minimum covering of G, a covering K is said to be minimum if G has no covering K dash such that the number of elements in K dash always less than the number of elements in K. For example, in the above graph, that is these 3 edges incident at the one end in 1 and these 3 edges are incident at 4 and 6, these are in middle edges are all incident in 6 and one more edge is not covered, that is 2, 3. We have to choose 2 or 3. Here we choose 2. Therefore, this K is a covering of G. Next, K dash 2, 4, that is these 3 edges incident at 2 and these 3 edges has one end at 4 and 5, 6, that is in 6, these all edges incident at 6 and 5, 6, that is 1, 5, we choose 1 or 5, here we choose 5. Therefore, K dash is a minimum covering of G. K1, that is here we see K1 equal to containing all the vertices, that is containing all the vertices, it will cover all the edges. Therefore, this is also a covering. K2, this is also a covering, but it is not minimum covering. That is, any covering, minimum covering means a covering which is less than this number of elements, then we will say that the covering is a minimum covering. But here we cannot find any covering having less than 4 elements. Therefore, this K dash, K double dash are minimum covering of G. The covering number means the number of elements in the minimum covering is the covering number of a graph. Therefore, for this graph, covering number of G is 4. That is, which is denoted by beta of G. Edge covering set. Edge covering set is a subset of E such that every vertex of G is incident with at least one edge of the edge covering set. That is, edge covering do not always exist. Since without edges the graph exists, therefore edge covering do not always exist. The graph has an edge covering if and only if delta greater than 0. That is, minimum degree of the graph always greater than 0, then only the graph has an edge covering. The complement of a matching need not be an edge covering. Complement of an edge covering need not be matching. But perfect matching implies edge covering. Perfect matching perfect matching means that it contains the edges which covers all the vertices of the graph. Therefore, this is the edge covering. Covering number. The number of vertices in a minimum covering of G is called G and covering number of G, and it is denoted by beta G. Edge covering number. The number of edges in the minimum covering set is called edge covering number of G, and it is denoted by beta dash of G. We consider these two examples. Here the edge covering, that is edge covering, these two edges covers these elements, and these two edges covers these four vertices. Therefore, beta dash equal to these four edges. That is beta dash minimum covering these four edges in the edge covering. Therefore, beta dash number of elements in the minimum edge covering is 4. Here, vertex covering, that is alpha dash edge independent set, that is edge independent set. These three edges, this edge and this edge and this edge are non-adjacent. Therefore, the number of edges in the maximum edge independent set is 3. Therefore, alpha dash is 3. A set S contained V is an independent set of G if and only if V minus S is a covering of G. S is independent set of G. That is, every element in any two elements in S are non-adjacent. Therefore, no two vertices of S are adjacent in G. Therefore, no edge of G has both ends in S. Suppose if edge has both ends in S, they are adjacent. Therefore, it is not possible. Therefore, no edge of G has both ends in S. Every edge of G has at least one end in V minus S. Therefore, V minus S is a covering of G. Next, we have proved that is vertex independent number and edge independent vertex covering number equal to gamma. The sum of the vertex independent number and vertex covering number is equal to the number of vertices in the graph. Let S be the maximum independent of set of G and K be the minimum covering set of G. That is, maximum independent set, the number of elements is denoted by, that is number of elements in S is denoted by alpha, that is independent number. Vertex independent number is denoted by alpha. Therefore, mod S equal to alpha. K minimum covering. Therefore, number of elements K is denoted by beta. Therefore, modulus of K equal to beta. Since S is independent set of G, by previous theorem, S is independent set, V minus S is a covering of G. K is covering of G if and only if V minus S is a covering of G. Therefore, K is a covering of G, then V minus K is independent set of G. Now, S is the independent set of G. S is independent, V minus K is a covering. Therefore, V minus K, that is, S is independent set, V minus K is also independent set, but S is maximum independent set. Therefore, the number of elements V minus, suppose V minus K is a maximum independent set, then the number of elements in V minus K equal to number of elements in S. Otherwise, that is, this is an independent set, this is a maximum independent set, then number of elements in V minus K is less than number of elements in S. Therefore, the modulus of V minus K is less than modulus of S. The modulus of S is denoted by alpha. Therefore, modulus of V minus modulus of A less than or equal to alpha. This is the number of vertices. Number of vertices in the V graph is gamma, and number of vertices in the minimum covering is beta. Therefore, gamma minus beta less than or equal to gamma. Therefore, gamma less than or equal to alpha plus beta. Here S is an independent set, therefore V minus S is a covering. So V minus S is a covering, the K is a minimum covering. We let us suppose that K is minimum covering. Therefore K is minimum covering, V minus S is a covering. Suppose V minus S is a covering, then number of elements in V minus S and number of elements K are equal. Otherwise, number of elements in V minus S is greater than number of elements in K. Therefore, the number of elements K is denoted by beta. Therefore, number of elements in V, number of elements in S greater than beta. Number of elements V is gamma and number of elements in S is alpha, which is greater than or equal to beta. Therefore, gamma greater than or equal to alpha plus beta. So from 1 and 2 we have all gamma less than or equal to alpha plus beta, gamma greater than or equal to alpha plus beta, therefore alpha plus beta equal to gamma. Now delta greater than 0, then only the edge covering exists and the edge independent set also exists. If delta greater than 0, then alpha dash plus beta dash equal to gamma, that is edge covering number plus edge independent number equal to number of vertices in the graph. Let M be the maximum matching in G. Maximum matching is nothing but maximum independent set in G. Edge independent set in it. Let M be the maximum edge independent set. Matching implies edge independent. That is maximum edge independent set in G. Let U be the set of all M unsaturated vertices in G. So these vertices are not in M, not in the edges of M. Let E dash denote the set of mod U edges incident with vertices of U. Let delta greater than 0 such a set exist. Suppose U be the unsaturated vertices of G. In M it contains, that is a maximum number of elements, that is maximum matching in G. The number of elements in maximum matching is alpha dash. Therefore alpha dash edges, M contains alpha dash edges. Each edge has 2 vertices. Therefore in M we have 2 alpha vertices of G. So then M union E dash is an edge covering of G. That is E dash denote the set of all U mod U edges incident with vertices of U. So gamma minus 2 alpha vertices are remaining. Therefore the U edges are incident that vertex set E dash. Therefore M union E dash is an edge covering of U. M is the edge set and E dash is the edge set, which are E dash is the edge set which are incident at the M unsaturated vertices of G. Therefore M saturated vertices are covered by M, unsaturated vertices are covered by E dash. Therefore the total M union E is an edge covering of G. Suppose beta dash is a minimum edge covering. Therefore, suppose M union E dash is a minimum edge covering, then it is the number of vertices in M union E dash equal to beta dash of G. Otherwise, modulus of, that is number of elements in M union E dash is greater than beta dash of G. That is mod M plus, that is in number of vertices in E dash is gamma minus 2 into alpha dash, that is mod M, which is greater than beta dash. That is in maximum matching, all edge independent number is alpha dash of G plus gamma minus 2 into alpha dash of G, which is greater than beta dash of G. Therefore beta dash less than or equal to modulus of M union E dash implies alpha dash plus beta dash less than or equal to gamma. Let us call this as 1. Now let us consider L be the minimum edge covering of G. Next we consider the set heights, which is the graph induced by the edges of L. Let M be the maximum matching in G. M be the maximum matching in heights. U be the set of unsaturated vertices in heights. Since M is a maximum matching, height of U has no links. Therefore, mod U less than or equal to modulus of L minus M, which is equal to modulus of L minus modulus of M. Also, mod U equal to gamma minus 2 into mod M. Since height is a subgraph of G, M is a matching in G. So, these discussions are all in heights. Since height is a subgraph of G, M is a matching in G. Therefore, gamma minus 2M less than or equal to mod M, that is mod U equal to mod L minus mod M, and mod U equal to gamma minus 2M. Therefore, we comparing these two, gamma minus 2 mod M less than or equal to mod L minus mod M, which is equal to gamma minus 2 plus M, that is gamma minus mod M less than or equal to mod L. Therefore, gamma less than or equal to mod L plus mod M. Therefore, alpha greater than, we also know that is M is a maximum matching in heights. Alpha dash is the number of elements in the maximum matching of G. Therefore, alpha dash is always greater than or equal to number of elements in the maximum matching of in heights. This is the maximum independent number in G. This is the maximum independent number in heights. Therefore, edge independent number in heights. Therefore, alpha dash always greater than or equal to modulus of M. Therefore, alpha dash plus beta dash greater than or equal to mod L plus mod M greater than or equal to gamma. Therefore, alpha plus beta, that is alpha plus beta always greater than or equal to gamma. This is called, we call it as 2. From 1 and 2, alpha dash plus beta dash equal to gamma. So, in a bipartite graph G, with delta greater than 0, that is minimum degree of the graph is always greater than 0, the number of vertices in a maximum independent set equal to number of edges in the minimum edge covering set. That is, number of elements in the maximum independent set is alpha, vertex independent set. The number of elements in the maximum vertex independent set is alpha, and number of edges in the minimum edge covering set is beta dash. Edge covering set is beta dash. Let G be a bipartite graph with greater than delta greater than 0. We know that alpha plus beta equal to gamma and alpha dash plus beta dash equal to gamma. We have already seen two theorems, alpha plus beta equal to gamma, alpha dash plus beta dash equal to gamma. So from this, gamma equal to alpha plus beta, gamma equal to alpha dash plus beta dash, therefore they are equal, alpha dash plus beta dash equal to alpha plus beta. By Koenig-Minimax theorem, in a bipartite graph G, the number of edges in the maximum matching is equal to the number of vertices in the minimum covering. This we know. Therefore, from this, that is number of edges in the maximum matching equal to number of edges in the maximum matching is alpha dash, and the number of vertices in the minimum covering is beta. Therefore, beta equal to alpha dash. Therefore, alpha dash plus beta dash equal to, instead of beta we put alpha dash. Therefore, alpha dash cancel, beta dash equal to alpha. So, therefore, the number of vertices in the maximum independent set equal to number of edges in a minimum edge covering set. Next, we will see the clique of a graph. Clique of a simple graph G is a subset S of V such that G of S, the graph induced by the vertex set of S, is a complete graph. That is, S is a clique of G if and only if S is an independent set of G complement. S is a clique of G. Therefore, the vertex set of S induced by the graph G is always complete. Therefore, complete implies any two vertices in S are adjacent in G. Any two vertices in S are non-adjacent in G complement. That is, the vertices adjacent in G are non-adjacent in G complement. Therefore, S is an independent set of G complement. Next, let us see the Ramsey number. Given any positive integer k and L, there exists a smallest integer r of k, L such that every graph on r of k, L vertices contains either a clique of k vertices or an independent set of L vertices. The number r of k, L is known as Ramsey number. That is, the smallest integer r of k, L such that every graph on r of k, L vertices contains either a clique of, that is, complete graph on k vertices or an independent set of L vertices. Now let us see r of 1, 1. R of 1, 1 is the smallest integer. That is, what is the smallest value of r of 1, 1, which is equal to 1. Since 1 is the smallest integer, that is, r of 1, 1 means that the graph on r of 1, 1 vertices which contains the clique of 1 vertices are independent set of 1 vertices. That is, since 1 is the smallest integer such that any graph containing 1 point contains k1 as well as k1 complement. Because k1 and k1 complement are the single point. Therefore, R of 1 comma 1 equal to 1. Next R of k comma 1. R of k comma 1 equal to 1. Since 1 is the smallest integer such that this means this number, the graph on this number contains clique of k vertices. A complete graph on k vertices are independent set of one vertex. With one point contains k1 complement. That is, 1 is the smallest integer such that any graph with one point contains k1 complement. Therefore, k1 complement. R of 2 comma 1 equal to 1. 1 is the smallest, that is with the graph on this number which contains k2, that is complete graph on 2 vertices or complete independent set of 1 vertices. Independent set of 1 vertex. Therefore, all independent set 1 k1 complement, that is k2 or k1 complement. Since 1 is the smallest positive integer such that any graph with one point contains k1 complement always, therefore which is equal to always 1. R of k comma 2 equal to k. Since k is the smallest positive integer such that any graph with k vertices contains kk. That is, R of any graph on R of k comma 2 vertices which contains kk, that is a complete graph on k vertices are independent set of 2 vertices. Since k is the smallest positive integer such that any graph contains, that is which contains the complete graph on k vertices, therefore which is equal to k. That is, which is the smallest integer. That is, R of 2 comma 2 means it contains complete graph on 2 vertices or independent set of 2 vertices, therefore which is equal to R of 2 comma 2 equal to 2. Suppose R of 3 comma 2 equal to, we get 3. That is, every graph on this number, that is R of 3 comma 2. Now let us see R of 3 comma 2. Let us consider the number R of 3 comma 2. The graph on 3 comma 2 vertices let us take 3 vertices graph. The 3 vertices, the graphs on 3 vertices, that is complete graph, and this graph and this graph, and this is the k3 complement. So here we see the R of k3 comma 3. So this graph contains k3. So this graph contains k2, that is independent set of 2 vertices, and this graph contains k2 and this graph contains k2. Therefore, R of 3 comma 2 equal to 3. For any two integer k greater than or equal to 2 and L greater than or equal to 2, R of k comma L less than or equal to R of k comma L minus 1 plus R of k minus 1 comma L. Furthermore, if R of k comma L minus 1, R of k minus 1 comma L are both even, then strict inequality holds. Now let G be a graph with R of k comma L minus 1 plus R of k minus 1 comma L vertices. Let B be any vertex in G. Let G be a graph with this number of vertices and V be any vertex in G. Then V can be non-adjacent to the set of at least R of k comma L minus 1 vertices, or V is adjacent to the set of R of k minus 1 comma L vertices. Since the number of vertices to which V is non-adjacent plus the number of vertices to which V is adjacent equal to the total number of the graph. Case 1. If V is non-adjacent to set S of at least R of k comma L minus 1 vertices, that is the vertices set this set induced the graph G of S contains either a clique of k vertices or independent set of L minus 1 vertices. Now V is non-adjacent with this G of S, the vertices, the G of S which contains either clique of k vertices or independent set of L minus vertices. Suppose G of S union V, that is G of S union V contains, that is V is non-adjacent with R of non-adjacent to S, Therefore, the set of all vertices S union V contains either clique of K vertices or independent set of L vertices. That is, V is non-adjacent with this. Therefore, K vertices as well as L minus 1 independent vertices. V is non-adjacent with these vertices. Therefore, V is independent with this number of vertices. Therefore, it contains either clique of K vertices or independent set of L vertices. That is, V joined by V is combined with L minus 1 vertices. They are all independent vertices. Therefore, G contains either a clique of K vertices or an independent set of L vertices. Therefore, R of K comma L less than or equal to R of K comma L minus 1 plus R of K minus 1 comma L. Next case, V is adjacent to a set of T of at least R of K minus 1 comma L vertices, then G of T contains either a clique of K minus 1 vertices or independent set of L vertices. If V is adjacent to a set T of at least R K minus 1 comma L vertices, then G of T contains either clique of K minus 1 vertices or independent set of L vertices. This V is adjacent. Therefore, the graph induced by the vertices capital T union V contains either clique of this V is adjacent to this K minus 1 vertices. Therefore, it forms a clique of K vertices. Therefore, it contains either a clique of K vertices or independent set of L vertices. Therefore, G contains either a clique of K vertices or independent set of L vertices. Hence, R of K comma L less than or equal to R of K comma L minus 1 plus R of K minus 1 comma L. In both the cases, we proved the result. Suppose these two numbers are both even. These two numbers are both even. Their addition is also both even. Therefore, let G be a graph on addition of these even numbers minus 1 vertices. That is odd number of vertices. G be a graph on odd number of vertices. Since G has odd number of vertices of even degree, odd number of vertices of even degree, G has some vertex V of even degree. Therefore, V cannot be adjacent to exactly R of K minus 1 comma L minus 1 vertices, or adjacent to R of K comma L minus 1 vertices. In either case, that is by previous cases 1 and 2, G contains either clique of K vertices or an independent set of L vertices. That is R of K comma L less than or equal to R of K minus 1 comma L minus 1 plus R of K comma L minus 1. Therefore, R of K comma L, which is less than or equal to, by previous theorem, so we have this result. Therefore, we omitting this minus sign, we get R of K comma L less than R of K comma L minus 1 plus R of K minus 1 comma L. Next problem, we consider R of 3 comma 3 equal to 6. Prove that R of 3 comma 3 equal to 6. That is, R of 3 comma 3 is the smallest positive integer. The graph on this integer contains no clique of 3 vertices or no independent set of 3 vertices. That is, R of 3 comma 3 is always greater than or equal to 6. Since in the graph on 5 vertices, we consider the pentagon. That is pentagon, the graph on 5 vertices. Here we don't have clique of 3 vertices and independent set of 3 vertices. Therefore, any graph existing this is R of 3 comma 3 is the minimum smallest integer which is having clique of 3 vertices and independent set of 3 vertices is always greater than or equal to 6. By Herodotus theorems, that is by previous theorem, R of K comma L less than or equal to R of K minus 1 comma L plus R of K comma L minus 1. Therefore, 3 comma 3, R of 3 minus 1 comma 3 plus R of 3 comma 3 minus 1, R of 2 comma 3 plus R of 3 comma 2. We have already seen R of 3 comma 2 and R of 2 comma L. r of 2 comma 3 plus r of 3 comma 3 are equal. R of 3 comma 3 is r of 3 comma 2 is 3 and r of 2 comma 3 is 3. Therefore 3 plus 3 r of 3 comma 3 is equal to 6. Now let us see this example. Here we consider that is 3, that is complete r of 3 comma 2. That is r of 3 comma 2 means the graph containing 3 vertices which contains the clique of 3 vertices. This is possible. Here only clique of 3 vertices or independent set of 2 vertices exist. Here also independent set of 2 vertices exist. Independent set of 2 vertices exist. Therefore r of 3 comma 3, r of 3 comma 2 is 3. Therefore r of 3 comma 2 is 3 as well as r of 2 comma 3 is also 3. We know that r of k comma l always r of k comma l equal to r of l comma k. Therefore r of 2 comma 3 and r of 3 comma 2 are equal. 3 plus 3 6. Therefore r of 3 comma 3 is less than or equal to 6. Here r of 3 comma 3 is always greater than or equal to 6. From this figure it cannot be 5. Therefore the r of 3 comma 3 is greater than or equal to 6. From 1 and 2, this is greater than or equal to, this is less than or equal to 6. Therefore r of 3 comma 3 equal to 6. Ramsey graph, that is k comma l. Ramsey graph is a graph on r of k comma l minus 1 vertices which contains neither a clique of k vertices nor a independent set of l vertices. Pentagon is a Ramsey graph. It contains neither a clique of k vertices nor an independent set of l vertices. Now prove that r of 3 comma 4 equal to 9. The 3 comma 4 Ramsey graph neither contain a clique of 3 vertices or an independent set of 4 vertices. Therefore r of 3 comma 4 always greater than or equal to 9. Then by Arrhenius-Casares theorem, r of 3 comma 4 less than or equal to r of 3 comma 4 minus 1 and r of 3 minus 1 comma 4 which is less than 10. Therefore r of 3 comma 4 equal to 9. Prove that r of 3 comma 5 equal to 14. 3 comma 5 Ramsey graph neither contains a clique of 3 vertices nor an independent set of 4 vertices. Therefore r of 3 comma 5 greater than or equal to 14. Then by Arrhenius-Casares theorem, r of 3 comma 4 is r of 3 comma 4 that is 5 minus 1 plus r of 3 minus 1 comma 5. 3 comma 4 is 9 and 2 comma 5 equal to 5. Therefore r of 3 comma 5 is less than or equal to 14. These two we have r of 3 comma 5 equal to 14. Next Arrhenius theorem, prove that r of k comma l less than or equal to k plus l minus 2 c k minus 1. That is NC2, NC2, NC3. Likewise k plus l minus 2 c k minus 1. Let us prove this theorem by induction on k plus 1. Let induction on k plus l. That is k plus l less than or equal to 5. We know that r of 1 comma 2 1, r of 1 comma 3 1, r of 1 comma 4, r of 2 comma 1 1. Next r of 2 comma 2 2, r of 2 comma 3 3, r of 3 comma 1 1, r of 3 comma 2, that is any r of k comma 2 is k. Therefore r of 3 comma 2 3, r of 4 comma 1 1. So sum of this is that is 1 plus 3 3, 4 5 3 4 5 4 5 5. Therefore l plus k less than or equal to 5. We have satisfies this condition, that is r of k comma l less than or equal to k plus l minus 2 k minus 1 k minus 2 c k minus 1. Therefore the result is true for k plus l less than or equal to 5. Let m and n be positive integer. Assume that the theorem is true for all integers k and l such that that is which we have verified the result k plus l less than or equal to 5. Therefore, greater than 5 we have to check it. That is 5 we have to prove it. That is 5 greater than k plus l less than m plus n. We prove the result for k plus l equal to m plus n. By induction hypothesis, R of k plus L, that is by Cicero's theorem, R of k less than or equal to R of k comma L minus 1, R of k minus 1 comma L. Here R of k comma L minus 1 plus R of k minus 1 comma L, which is less than R of k plus L minus 1, which is less than k plus L. Therefore, we apply the induction. By induction, that is the result R of k comma L is less than k plus L minus 2 minus k minus 1. Therefore, here k plus L minus 1 minus 2 C k minus 1. For this k minus 1 plus L minus 2 C k minus 2. Here sum of this k plus L minus 3 k plus L, that is the k plus L minus 3 k minus 1 C k minus 1 C k minus 2. That is NCR plus NCR minus 1 equal to N plus 1 CR. Using that formula, we have k plus L minus 2 C k minus 1. So, hence the result proved. Next, prove that R of k comma k greater than or equal to 2 power k by 2. K greater than or equal to 2. We know that R of 1 comma 1 equal to 1 and R of 2 comma 2 equal to 2. Let k greater than or equal to 3. Let script Gn denote the simple graph with vertex set v1, v2, etc. vn. The set of simple graphs formed by these vertices are denoted by the script Gn. And Gnk denote the set of all graphs in Gn, that is the simple graph formed by these vertices. All the simple graph formed by these vertices are denoted by Gn, and in Gn, Gnk denote the set of those graphs in Gn with clique of k vertices. This set of in these simple graphs, the graphs which are having the clique of k vertices, we will collect that the graphs having clique of k vertices, we denote it by the script Gn of k. Any simple graph with v1, v2, etc. vn vertices is decided by its edges. That is, they are differ only by the edges. Because all the graphs are having the vertices v1, v2, etc. vn. That is, we are all the simple graphs having the vertices n, these n vertices. They are only differ by the edges. They get from NC2 lines. That is, in any complete graph we have NC2 lines. Therefore, these NC2 lines will decide the simple graphs. Therefore, they get from NC2 lines in Gn complete graph with n vertices. That is Gn complete graph with n vertices. This NC2 line in Gn complete graph with n vertices. Therefore, number of graphs in Gn equal to, that is 2 power nc2. That is number of elements decided by nc2 lines. Therefore, the power set 2 power nc2 subsets exist. Therefore, the number of simple graphs in Gn equal to 2 power nc2. Similarly, any simple graph with this set of vertices with the clique of k vertices is decided by these edges. They get from, that is nc2 lines minus kc2 lines. Therefore, the number of edges of a clique of k vertices is kc2. That is, the number of edges of a clique of k vertices is kc2. Therefore, the number of graphs in Gn having a clique of particular set of k vertices is 2 power nc2 minus kc2. Therefore, any set of k vertices can be selected from n vertices by nck ways. Here, I will explain. That is, similar in Gn, it is Gn is in Gn denote the set of all simple graph which are formed by the vertex set v1, v2, etc. vn. The simple graphs can be decided by its edges. The total number of edges in any graph is NC2 lines. Therefore, NC2 lines can be from the NC2 lines we have decide the simple graphs. Therefore, any simple graph, these vertices with the clique of k vertices is decided by its edges. Therefore, they got from NC2 line minus KC2 lines. Here the number of simple graph is 2 power, that is subset of the power set 2 power NC2 lines. That is the number of edges, edge set is the number of edge set is NC2, the power set is 2 power NC2. Therefore, the number of simple graph is 2 power NC2 power simple graphs. The simple graph with this vertices with the clique of k vertices is decided by its edges. Its edges is NC2 lines minus KC2. Therefore, the number of edges of clique of k vertices is KC2. Therefore, NC2 minus KC2. Therefore, the number of graphs in Gn having clique of particular set of k vertices is the power set 2 power NC2 minus KC2 graphs. Any set of k vertices can be selected from these n vertices by NCK ways. Therefore, number of simple graph containing clique of k vertices is NCK into 2 power NC2 minus KC2. Therefore, number of simple graph with the clique of k vertices divided by number of the simple graph is equal to NCK into 2 power NC2 minus KC2 divided by 2 power NC2. That is NCK, here 2 power NC2, 2 power NC2, 2 power minus KC2. Therefore, this NCK can be written as n into n minus 1, n minus 2, n minus k plus 1 divided by this k factorial and 2 power KC2. That is KC2 means k into k minus 1 divided by 2. That is always n equal to n minus 1 greater than n is greater than n minus 1. We put n minus 1 instead of n. Therefore, here we are having less than n. This instead of n minus 1 we put n, instead of n minus 2 we put n, and n minus k plus 1 by n divided by k factorial into 2 power minus KC2. If n less than 2 power k by 2, 2 power k by 2, then this is less than n power k, that is this is 2 power k minus C2, n is less than 2 power k by 2, n is less than 2 power k by 2, n is less than 2 power k by 2 divided by k factorial. Therefore, n power k divided by k factorial into 2 power k minus k C2. That is 2 power, instead of n you put k by 2. That is n into n up to n k times. Therefore, n power k 2 power k C2. Here n is less than 2 power k by 2. Therefore, which is greater than 2 power, instead of n you put 2 power k by 2. K by 2 into k, that is k squared by 2 minus k into k minus 1 divided by 2. Here k factorial, that is 2 power k squared by 2. Here 2 power k squared by 2 minus plus k by 2. Therefore, k squared by 2, k squared by 2 cancel, 2 power k by 2 by k factorial, which is always less than 1 by 2. Thus, the number of graphs in Gn with clique of size k is less than the half of the number of graphs in Gn. Therefore, also in Gn, every Gn consists of all the simple graph which is complement also belongs to Gn. G and G complement also belongs to Gn. That is, Gnk is less than, that is 1 by 2 of modulus of Gn. That is, the number of graphs with the k isolated vertices is less than the number of graphs in Gn. That is, number of isolated vertices means independent set of k vertices is less than the half of the number of graphs in Gn. There are some graphs in Gn which contains neither a clique of k vertices nor independent set of k vertices. Therefore, if n less than 2 power k by 2, there are graphs having n vertices and they contain neither a clique of k vertices nor an independent set of k vertices. Therefore, R of k comma k is always greater than or equal to 2 power k by 2. That is, here we are having that all simple graphs, only the complement. If G exists, G complement is also exist. Every graph have complement is also in G. Therefore, Gn k is less than 1 by 2 of Gn. Gn means that is the simple graph having a clique of k vertices. Other side, that is the complement sides, here G and the graphs containing clique of k vertices less than half into G power half into the number of simple graphs. That is, in simple graphs we have G and G complement. If G has, if the graph has the clique of k vertices, then G complement has the independent set of k vertices. Therefore, they are equal. The number of graphs with k isolated vertices always less than the number of graphs in Gn. Therefore, the sum graphs in Gn which is not equal, that is which is less than. Therefore, there exists some graphs in Gn contains neither a clique of k vertices nor an independent set of k vertices. That is, G exists, G complement exists. In G, clique of k vertices exists, G complement, there exists independent set of k vertices exist, but we have modulus of, that is number of graphs with clique of k vertices always less than the half of the simple graphs. So they are not equal. So some graphs in Gn contain neither a clique of k vertices nor an independent set of k vertices. Therefore, if n less than 2 power k by 2, there are graphs having n vertices and they contains neither a clique of k vertices nor an independent set of k vertices. Therefore, R of k comma k greater than or equal to 2 power k by 2. That's all.